module deals with saline clays, especially magnesian saline clays, across a range of saline geosystems. In this first sectional chapter, we'll look at the transport of clays with a focus on arid zone processes and discuss whether eolian or fluvial transport mechanisms dominate and how they change with relative distance from the supply area. In the next section, we'll look at the various saline clays, their mineralogical variations in both the ladder structure and also in terms of their origins, if they are replaced or if they are a neoformed clay. Then we'll have a look in the following section at the salinity controls on both neoformed and homogeneous clays, whether there's a aluminosilicate precursor which has been altered or whether there is a clay forming as a magnesian clay coming out of solutions such as Stevensite. That's followed by the section which focuses in on the zeolites and the chert and the carbonate associations with the zeolite associations, how we form calcitic spherulites, dolomites, and how methanogenesis releases significant volumes of magnesium and silica into the diagenetic milieu. Lastly, we'll look at and summarise the various saline clay responses both to syn-depositional brine styles and hydrologies and the subsequent burial evolution of those clays. What's different when we look at saline clays versus the various transported clays, the eolites and the chlorites that deposit in environments with relatively fresh water or seawater? The prime difference is the level of magnesium in the system and the fact that we can form magnesian silicate clays where there was nothing there before. We can also alter pre-existing transported clays, such as eolite, by increasing the magnesium content into those clays. So the presence of these saline magnesian clay minerals is related to the elevated magnesium content in the brines. This could be true both in the surface waters where the clays are accumulating or in the subsurface where clays are being orthogenically altered by a crossflow of magnesium-rich mesogenetic or burial waters. We'll look at transport mechanisms in this section and we'll discuss what's dominant, the aeolian process or the fluvial process, remembering that in this association we are looking at systems where we can have water-covered extents at times of more than 1,000 kilometres. Whether flocks occur or whether we have aeolian transport is very much related to differences in the two mechanisms or the two transport processes, the fluvial transport versus the aeolian transport processes. We'll also have a look at how the freshening of the upper brine layer in a salinity-layered depositional association for evaporites, so this can be due to marine influx or stormwaters bringing in a fresher water content, is often followed by subaerial exposure as the water body dries up. It can also be the loss of layering due to the transition from meromictic to holomictic water columns. There's also the possibility that with freshening, if we have clays, if we dissolve the surrounding halite matrix, we can end up with a clay layer, which is in effect an insoluble residue on the bottom of a freshened brine body. That insoluble residue body can then be reworked by later aeolian, gravitational, or bottom water currents. So in this section, I want to focus in on how do we get clay into a saline sump. We'll look at orthogenic formation, the neoform clays, in the next sections. But for now, I just want to look at bringing in detrital clays, either by fluvial or aeolian transport. And remember that in most saline depositional associations, we're looking at these flood or fry associations, where we have desiccation and subaerial exposure, or at times we have flooding where we bring in a body of water. It can be marine-derived, it could be storm-derived, that covers that body of halite accumulation. Here's an example of the Jordan River, and we can see how that flooded Jordan River is carrying out clay in what are relatively fresh waters, being distributed and floating atop a more saline body of brine, which in the case of the Dead Sea is near or at halite saturation in the dominant water mass in the Dead Sea. So we have these floating water bodies, floodwaters, coming in less dense, carrying suspended load clays and floating atop that more dense Dead Sea water mass. That's true of the Jordan River. And it's also true of many of the surrounding waddies, which during flood times also carry in suspended sediment plumes. Here we can see a canyon mouth on the eastern side of the Dead Sea margin with a flood as it occurred in October 2014, bringing that detrital clay-rich plume out into the Dead Sea. What happens is that we get flocculation of clays at that mixing interface between the two water bodies. The composition of the initial clay sediments will depend on that suspended load carry in this situation. So we're bringing in a detrital load from the surrounding semi-arid or arid desert margins into our lacustrine depression. We have in effect a body of fresher water with a suspended load carrying colloidal clays, suspended load clays, and as a mixing interface with the underlying brines. Now that increased salinity, as was shown by Gregory and Amelia back in 1989, that saline interface between that upper fresher water body and that lower saline water body drives flocculation as it shrinks the electric double layer that's surrounding most clay minerals, which have a surface charge. Individual clay particles in colloidal suspension have a negative charge around their edges, with positive charges in their centers. And so that means the plates are going to have like charges on their outside forms, and so they're going to repel each other. If the water is saline, then the abundant sodium and chloride ions will neutralize that repulsive effect. They'll be attracted to those positive charges. And so what we then see is that the clays then aggregate or flocculate and settle into that salt water mass quite fast. And you can see that when those flocks form and settle, they sweep up the smaller particles and flocks between them. And so that means the flocks grow to a larger size, and ultimately we see, as we can see in this phosphorescent layer, that we form descending plumes where we have larger flocks. And so the incident flocks grow larger and they fall faster and they sweep up smaller particles, and we see these descending plumes. And of course that changes the settling dynamics, as you can see here, from hours or days to minutes. And of course once those clay flocks settle to the bottom, cohesion makes them stick together, and that's resistive to further remobilization. And so we get clay layers in the bottom sediments at times of flooding, where the flocculation is driven by that interface. The other transport mechanism that brings detrital clays into many saline depositional environments is aeolian transport. Most detrital clays that we see, certainly away from the margins where we see this flocculation effect as we bring in fresh water bodies into the margin, away from those margins, remember these bodies of deposition were 1,000 kilometres or more wide. Most of the clays we see in those basin central positions in evaporite deposits is aeolian transport, bringing in suspended in-air sediment to settle down through the water column. So most detrital clays in the central parts of the depositional system are probably wind-carried rather than water-carried detrital clays. We can see that today if we look at the Saharan air layer, and here we've got the dust optical depth averaged over the years 2003 to 2012, where we can see that that Saharan air layer is basically located above the trade wind inversion, the Hadley cell. It stretches from 1.5 to 7 kilometres in altitude above sea level. It's most pronounced during the northern hemisphere summer. So this layer of warm, dry air most of the time is dust layered, and it's carrying Saharan dust across the Atlantic toward the Americas. So this is an inversion layer that's bringing material from the Saharan desert into the Americas, into the Gulf of Mexico and into the Amazon. In the Lake Eyre Basin, we see similar things where the dust optical depth is a measure of atmospheric turbidity caused by the presence of the dust aerosol particles. It's usually calculated over the entire atmospheric column, and so it will depend on the dust concentration in that atmospheric column and the size distribution and its optical properties. So the dust optical depth is referring to the contribution of dust to the atmosphere. So a value of 0 indicates pristine, clear sky conditions, while values of 0.5 are associated with dusty haze, and values of 1 and larger indicate very hazy conditions. That dark green shaded portion on the image, which centres on the Lake Eyre basin, shows us the dust optical depth in the greens to reds, and we can see that there is a very strong dust effect in the Lake Eyre basin, that dark green area. And you can see that very widespread red area there is indicating that the Lake Eyre bainage is a global dust hotspot, and it's the largest dust hotspot in the southern hemisphere. There is a lot of aeolian dust moving into the atmosphere across that relatively vegetation-free area of desert. Aeolian transport can move detritus over significant distances. In Australia, it's moving it into the Tasman Sea to the southeast. Coming back to the Saharan air layer, in the Saharan air layer, it's transporting this fine debris over distances of 1,000 kilometres or more. So we're taking dust up into the atmosphere, and it's circulating. This is NASA imagery. And you can see that aeolian dust is actually moving fine detrital clay from the Sahara into the Amazon. A very large amount of dust is carried by the Saharan air layer into the Amazon basin. It's also thought that this dust, as you can see in the profiles here, which is moving into the Amazon, is carrying micronutrients which help fertilize that rainforest area. Dust is widespread in terms of its transport coming off arid zones into adjacent water bodies. We see it today in the Lake Eyre basin and in the Saharan air layer, and we see it at many times in the past. Here's the same effects on the ground around the Lake Eyre basin, which divided up into a terminal salina with halite coverage of the bottoms once the lake is desiccated or the playa is desiccated. And we've got imagery around the margin shown in positions A, B, C, and D, where in A we're seeing streamers, aeolian streamers downwind of islands within Lake Eyre. We can see in B aeolian material accumulating upwind and streaming around a variety of barrier islands. In C we're seeing shoreline aeolian streamers moving sediment into the adjacent desert area. It's one of the main feeders into the Strzelecki Desert. And in D, we can see aeolian material accumulating on the windward side on a variety of salt lows. The next image shows it even clearer. Here is that dust transport in action in a northerly directed wind stream in February the 2nd, 2005, and a easterly directed wind stream on October 28, 2003. So this sediment transport is aided by ephemeral salt growth in the vadose zone in the salt flats on these playas, which facilitates breakdown of the lake sediments, as we discussed in the previous section on sebkhas. Once we are above the capillary zone atop the water table, we see dispersal of windborne fines into aeolian transport. And here we can see it not just forming dunes, but also forming significant dust clouds in the overlying atmosphere. Aridity favours aeolian clay transport. Ancient trade wind belts tended to move dust into ancient saline seaways and mudflats. And we'll come back to this discussion when we look at Pangaea in our discussion of ancient evaporites. But in that very hyper-arid central part of the Pangaean supercontinent, which extended all the way across the equator, we had a range of aeolian source fines being deposited in the playas in the alluvial fan systems. You have to ask the question, in these very extensive ancient deposits in the Triassic of Europe and the Permian of North America, what proportion of those many structureless fine-grained clay beds is actually aeolian dust? Were those clays concentrated into bands via subaerial dissolution and brine freshening, where we just dissolved away the salt? Or were they aeolian transported? In either case, they're not tied to fluvial suspension. And we see abundant evidence of that vadose association with clays. When we see evidence like this, we see it in the Western Canadian potash deposits. We see it in the potash deposits in the Salado Formation in the Delaware Basin. These are images from the Salado Basin near the marker bed 118 and also between beds 128 and 129 polyhalite markers, where we can see subvertical to vertical clay-rich zones penetrating into the ore zones. This sediment must have been gravitationally influenced, must have been vadose, with gravity feed vadose dissolution allowing clay infiltration into the sediment to form these mud-filled pipes in and below what was a subaerial exposure surface. So these vertical extensions at the bed base suggest extensional cracking. It's very likely that the underlying salt was vadose at the time of infill. In summary, fluvial transport is aided by flocculation at saline freshwater interfaces. That process tends to be more significant around the margins of a playa or an ancient mega seaway, while in the central parts of a seaway, we tend to see aeolian transport bringing clays into the more distal portions of the seaway. And then superimposed on that, we have dissolution taking place where we can see clay beds which were once suspended in the halite, for example, as the halite dissolves, forming cumulate layers of insoluble residues between layers of subaqueous evaporite deposition. In the next section, we'll look at what happens to those detrital clays once they sit in these magnesium-rich brines.